Okay, so today we're going to take a look at a couple of basic root theorems. The first one is called the irrational root theorem, and it basically says that if a plus the square root of b is the root of any polynomial equation, then so is a minus the square root of b. So, and it comes with a little caveat here. It says this is true for even roots, but not for odd roots. So my basic explanation is this. So solutions with roots, okay, anytime you're going to do the square root, the fourth root, the sixth root, always come in pairs. Okay, they always come in pairs. And so when you think about the quadratic formula, all right, we have this quadratic formula. It's x equals negative b plus and minus the square root of something. Okay, obviously it's b squared minus 4ac all over 2a. But basically, whenever you have the negative b plus or minus, if there's any number that ends up in here, okay, it doesn't matter what that number is other than 0. If there's any number that ends up in there, you're going to get two solutions. So that's what this root theorem is saying. If you get a plus root b, then there has to be an a minus root b, and that includes negative solutions in the root too. Okay, the only number that wouldn't be true with is a plus or minus the square root of 0, because that wouldn't make sense. Okay, so think about that as we go through some of these. So really all we want to do is we want to be able to know how to use this when we're writing equations, when we're looking at polynomials on graphs, things like that. So it says identify the irrational roots of a polynomial with known roots of 3 plus root 2 and negative root 17. So I'm actually going to start off with the negative root 17. When they tell me I have a solution of x equals negative square root 17, okay, what I need to know right away is that implies there is another root of x equals positive, and I'm going to put the plus on this one, square root 17. So one implies the other. Okay, so when it tells me I have a root of 3 plus root 2, what it's telling me there is that I have this root of x equals 3 plus square root of 2, which means, based on the theorem above, the irrational root theorem, this implies that there has to be another solution of x equals 3 minus the square root of 2. Notice the 3 didn't change, only the plus and the minus in the middle. Again, go back to the quadratic formula. The negative b doesn't change. It's the plus and the minus after the negative b. So think about this 3 as the negative b value. Okay? So the next thing it says to do is write the equation of the polynomial in factored form. In order to do that, I need to put these guys back into factors. The way I put a solution back into a factor is I bring the number here back over with x. So I'm going to go ahead and add the square root of 17 to both sides here. Square root of 17. So I get x plus the square root of 17 equal to 0. I'm going to subtract the square root of 17 on this guy, on both sides. So I get x minus the square root of 17. So you can even see that the factors that I'm about to write, one's x plus the root of 17, the other one's x minus the root of 17. So these two guys can come down. So my polynomial equation, I'm just going to call it p of x. All right, you could call it f of x, you could call it y equals whatever, but it's going to have one factor of x plus square root of 17 and one factor of x minus square root of 17. Now, I've still got to finish up the other two because this equation has four solutions, so I need to bring the 3 and the root 2 over with the x. So I'm going to subtract 3 on both sides, and I'm going to subtract root 2 on both sides. So minus 3 minus root 2. So this gives me a factor of x minus 3 minus root 2 equal to 0. And take a look at the other factor here. The 3 is still positive, so I'm going to subtract root 3, but this time I'm going to add root 2. So subtract 3, add root 2, and I get x minus 3 plus root 2. So it's only the root that changes, that you have the plus and the minus. The other number out in front of the root, if it's 3 plus or 3 minus, then you keep the same sign there. So bringing those two roots down here, I have x minus 3 minus root 2, and the order of those doesn't matter, times x minus 3 plus root 2, and that would be my polynomial equation in factored form. So another similar theorem is the irrational root theorem, and I kind of mentioned this in the one above when I talked about negative roots, but it basically says that if a plus bi is a root of a polynomial, then so is a minus bi. So basically what that is when you do the quadratic formula again, or when you take a fourth root, you might end up with something like negative 3 plus and minus the square root of, I don't know, negative 2. That's an I value right there. So that would be an A plus and minus BI. So imaginary roots also come in pairs. All right. So let's take a look at an example with those guys. So it says identify the imaginary roots of a polynomial with known roots of 7 minus 3i and 4. So I'm going to start with 4 here. So if you look at the number x equals 4, that is not irrational. There's no I value, and it's not a root value. So it doesn't fit with my first theorem either. So there's nothing in here that implies that x equals 4, negative 4 is a root. So a whole number or a decimal or a fractional by itself does not imply x equals negative 4. So I'm not even going to worry about that. So if I have a root of x equals 4, then that means I have a factor of x minus 4. So there's one of my factors. But then I have to take a look at this other guy here. I've got x equals 7 minus 3i. So that does imply that there's an x equals 7 plus 3i. All right? So now I need to bring these guys back over. So I'm going to subtract 7 here, subtract 7 here. I'm going to add 3i here. I'm going to add 3i here. I'm going to subtract 7 here, subtract 7 here, minus 3i here, minus 3i here. So here we go. We got a lot going on here. We have x plus 3i minus 7 equal to 0. And we have x minus 3i minus 7 equal to 0. Again, the order of these guys really doesn't matter. Once you get used to doing them, you'll probably pick an order. But so here's my other factors. X plus 3i minus 7 and x minus 3i minus 7 equals, and this time I'll just use f of x for my value here. And it doesn't say it does say keep in mind to write it in factored form, so I don't have to worry about multiplying all that stuff out at this point here. Okay? All right. So some things about polynomials here. We're given a polynomial, 2x cubed plus x squared minus 7x minus 6. And this polynomial here is a third degree. So when it says how many total roots or solutions does f of x have, it has 3 solutions. All right, there are 3 solutions. 3 solutions. How do I know that? Because this is a third degree polynomial. 3 solutions because the largest exponent is 3. All right? It's called a third degree polynomial. All right? How many real roots could f of x have? So if you think about that, what they're saying is they're not talking about imaginaries here, they're talking about real roots. So when you see a polynomial, it could always have, if it's a third degree, it could have 3 real roots. If it's a 4th degree, 4. If it's a 5th degree, 5. It can always have as many real roots as the degree. So real roots we could have 3 real roots. All right? Again, same as the degree. Same as degree. All right? But when we talk about how many possible imaginary roots, okay, now you got to think that imaginary roots come in pairs. Okay? So how many possible imaginary roots? Well, there can only be 2 imaginary roots because imaginaries come in pairs. So if there's only 3 roots total, then there can only be 2 imaginaries. All right? So since there are 3 roots, and I'll say 3 solutions, means the same thing, 3 solutions, then only 2 of them could be imaginary. All right? Hopefully that makes sense. That if I have 3 solutions and I can only have 2 of them as imaginary. Yep, I learned how to spell and talk at the same time here. Imaginary. All right? So if it was a 4th degree polynomial, I could have 2 sets of 2 imaginary solutions for a total of 4 imaginaries. Okay? What is the least number of times f of x could cross the x-axis? All right? So it could cross the x-axis only once. One time. How do I know that? Because if 2 solutions are imaginary, like we talked about above, if 2 solutions are imaginary, then the 3rd solution is real and touches or crosses the x-axis. All right? And we would end up with something that looks like this. If you had a 3rd degree polynomial like the one up above and it only had 1 real solution, it might look something like this. That's a 3rd degree polynomial there. It's got the right number of turns and curves, and it only touches the x-axis at 1 point. All right? So the last question says, how many times could f of x cross the x-axis? Okay? So, well, it could cross 3 times. So 3 times would be the max. All right? And the reason is because if f of x has 3 real solutions, then it, and I'm going to say 3 real distinct solutions. So when I say distinct, I mean like x equals 1, x equals 2, x equals 3. Okay, so we wouldn't have x equals 1 and x equals 2 and another x equals 2. All right, and we'll talk about this more in some of the upcoming lessons. But if it's got 3 distinct real solutions, then it crosses the x-axis 3 times. All right, x-axis 3 times. All right. If if there were 2 imaginary solutions, just like what we talked about above, what is the least number of times it could cross? If there were 2 imaginary solutions, then it would only cross 1 time. So we address that. Okay? And then one of the other things that we'll talk about again is when we get repeated roots. What happens when we have x equals 2, and that's, again, you get, let's say you get x equals 1, x equals 2, and then the 3rd solution is also x equals 2. In that case, we only touch the x-axis twice. Okay? That's it.
Alrighty then.